In these two videos, we will discuss uniform continuity. We will learn how to recognize if a function is or is not uniformly continuous just by looking at its graph. We will learn how to visualize uniform continuity, and we will learn how to prove that a function is or is not uniformly continuous by looking at insightful examples. So let's begin with the definition of uniform continuity. So let f from ab to r be a function. So of course, here ab is just an open interval and it is not empty. So a is less than b. And let I be a subset of ab. I is non-empty. So we say that the function f is uniformly continuous on the set I. So the function f is uniformly continuous on the set I if, and here is the definition, if for every epsilon greater than 0, there exists a number delta greater than 0, such that whenever we choose 2 points, x1 and x2, inside of this set I, as soon as the distance between these 2 points, the absolute value of x1 minus x2 is less than delta, we know that the distance between the values of the function at these 2 points is less than epsilon. So the distance between the values of this function on these 2 points will be absolute value of x1 minus f of x2, absolute value of f of x1 minus f of x2 is less than epsilon. So this is the definition of uniform continuity. All right, let us compare this definition to the definition of continuity of the function f on the set I. Because this definition, I'm going to call it 1, this definition 1, it probably looks awfully familiar to us. It looks almost like the definition of a continuous function. So the function f is continuous on I if and only if f is continuous at each point x1 in I. You remember that, right? So a function is continuous on a set if and only if it's continuous at every point of that set. If and only if, and here is the definition. So at every point x1 of this set I, f is continuous at this point x1. So now I'm going to write down the definition of continuity of the function f at the point x1. So for every epsilon greater than 0, there exists delta greater than 0, such that for every point x2 in I, if the distance from x2 to x1 is less than delta, then the distance from f of x1 to f of x2 is less than epsilon. So this is the definition of the statement that the function f is continuous on the interval I. So now let us look at this definition 1 and the definition 2. And let's compare. They look almost the same, except you might notice that in the definition 2, we see for every x1 in the beginning of the definition. And in the definition 1, we see for every x1 somewhere in the middle of the definition. That's truly the whole difference. Let's just try to understand what does that mean. So if we look at this delta in definition 1, this delta has nothing to do with x1 in the definition 1. However, if we look at the delta in the definition 2, it looks like this delta may depend on x1. So this is the major difference between these two definitions. So difference so in definition 1, the number delta only depends on epsilon, and delta does not depend on x1. So this is how I denote it. When I write delta equals a delta of epsilon, it means that delta is a function of epsilon. But delta does not depend on x1, and I denoted this by writing delta does not equal a function of x1. And then in definition 2, it appears that delta is a function of both epsilon and x1. So in other words, in uniform continuity, in the definition 1 of uniform continuity, this delta does not depend on the point x1. We have the same delta for all x1 and x2. So let us now discuss the visualization of uniform continuity. So let us consider this example here. So I'm going to ask you to trust me for now that the function f of x equals to x squared is uniformly continuous on the interval 0, 1. We are going to prove this later, so don't worry. This is a rigorous lesson and a rigorous explanation, but for now I'm just asking you to accept that this is the fact, and instead of proving this, we are going to discuss what this means in terms of the graph of the function that is plotted right here. The graph of the function y equals to x squared is plotted here, and we know that this function is uniformly continuous on the interval 0, 1. So of course we know that graphically what it means that the function is continuous is that we do not see any sort of, to say, gaps in the graph. So we can draw the curve without taking off the pencil from the paper. Let us now discuss what it means graphically or visually that this function is uniformly continuous on the interval 0, 1. So first of all, let us elaborate on this fact, on this statement. What does this mean that the function f of x is uniformly continuous on the interval 0, 1? So if we fix epsilon greater than 0, for that epsilon, definition 1 holds. So definition 1 is the definition of uniform continuity. We can all go back and look at the definition 1, and it's right here. I'm underlining it for you. Can you see that? So whenever I fix an epsilon greater than 0, there exists a delta greater than 0 such that for every x1, x2 in the interval I, so what's the interval I for us? It is 0, 1, isn't it? So for every x1, x2 in the interval 0, 1, as soon as the distance between x1 and x2 is less than delta, the distance between the values f of x1 and f of x2 is going to be less than epsilon. Now, what is f of x for us in our example? It is f of x1 is x1 squared. F of x is x squared. So let's go back and write this down, the meaning, just by this definition that we have just say. So by definition 1, there exists delta greater than 0 such that for each pair x1, x2, pair of points on the interval 0, 1, as soon as the distance between x1 and x2 is less than delta, the distance between the values of the function, so those would be x1 squared and x2 squared, is less than epsilon. All right, so this is the meaning. So now let's just think about the following the following things. So at this point, we have a number epsilon greater than 0. We picked it. And we also have a number delta greater than 0. So we picked these two numbers. So for this epsilon, there exists a delta. So our numbers epsilon and delta greater than 0 are fixed at this point. So for these two numbers, I'm going to ask you to consider this cylinder over here. So delta right here is the height of the cylinder, and epsilon right here is the diameter of the cylinder. So what it really means visually, that the function f of x equals to x squared is uniformly continuous on the interval 0, 1 is the following. I can take this cylinder right here and I can imagine that my graph right there is made out of wire, but in such a way that I cannot bend the wire. And I can take that cylinder and I can thread that wire through like this. Do you see? So this wire is inside the cylinder. Okay? So here I have this is a bigger scale for you to see. So this curve right here, it's like made out of wire, and this wire, which is the graph, is inside the cylinder. And the meaning of the fact that the function f of x equals to x squared is uniformly continuous on the interval 0, 1 is the following. Of the fact, and I'm gonna call it fact star. If the curve is made out of wire, perhaps I'm not gonna write this down. We can drag the cylinder along the curve while not rotating the cylinder, or so it means that the side or all of the sides of the cylinder remain horizontal. Okay, so we can thread it. So I just want you to look at the graph one more time. So here is the graph. What does it mean that we can thread the cylinder or drag it like that? It just means that I can go ahead and move the cylinder along the curve like this. And I will be able to do so without having to turn the cylinder and without having to turn the curve. So this is a visualization, and now that we have considered it, we are going to prove this statement here, this fact that I asked you to believe in it for a while. Now we are going to prove it rigorously. So let us prove that f of x equals to x squared is uniformly continuous on 0, 1. So let us recall what is the definition of uniform continuity of the function f of x equals to x squared on 0, 1. So f of x equals to x squared is uniformly continuous on 0, 1, if and only if for every epsilon greater than 0, there exists delta greater than 0, such that for every x1, x2 in the interval 0, 1, as soon as the distance between x1 and x2 is less than delta, we have that f of x1, which is x1 squared, minus f of x2, which is x2 squared, and the absolute value of that difference is less than epsilon. So the distance between the values of the function at x1 and x2 is less than epsilon. So this is just the definition of uniform continuity, but it is applied to the specific case of the function f of x equals to x squared on the interval 0, 1. So the fact that we are using this specific case is reflected in that instead of any interval, we are writing the interval 0, 1, and here we used x1 squared and x2 squared, okay? So let us reflect on this, what we have just done here. So whenever we need to prove something, the first thing that we need to do is to recall what the definition of that statement is, right? So we need to prove that the function f of x equals to x squared is uniformly continuous on 0, 1. So where do we start? We just start with the definition, right? So this is why it is so important to remember definitions, because if we do not remember definitions, we just do not know where to start. So this is why I encourage you to memorize the definition of uniform continuity. And actually, it's helpful not to memorize definitions just blindly, but to understand where the definitions are coming from. So this is why we have discussed this intuitive understanding of uniform continuity using the cylinder that we can drag through the graph of the function if it was made of a wire. So remember, we have to drag the cylinder in such a way that its sides are always horizontal, all right? So one more time, I just want to encourage you to memorize the definition of uniform continuity, and not just blindly, but with intuitive understanding. Because if you remember the intuitive understanding about the cylinder, you will always be able to write down the definition. If you just memorize it as a bunch of symbols, it is likely that after some time you're going to just forget the definition. So it's important to understand the definition in order to really remember it for a long time. Okay, so let's just come back to this example. So this is our proof. Let us start our proof, and let's just start with a strategy. So this is Scratch. So normally we don't have to write down the strategy. However, this is the first time we are proving in this lesson that a function is uniformly continuous. And so it's important that we understand what the strategy of our proof is going to be. So all we have to do is to prove this statement. I'm just going to call it 1. I'm going to start numbering independently here. So our strategy is to prove statement 1, okay? So let's go ahead and, so this is end of Scratch. So in order to prove statement 1, we have to fix epsilon greater than 0. When we want to prove that something is true for every epsilon greater than 0, what we usually do is we fix a positive number and then we carry out our proof. And if we are able to carry out the proof for an arbitrary epsilon, it's it means that we actually proved that the statement is true for every epsilon greater than 0. So let's just write down what we need to show. It's good to know what is it that we are after, so that we kind of have a direction for our proofs. So we want to show that there exists delta greater than 0, such that for every x1, x2 in 0, 1, as soon as the distance between x1 and x2 is less than delta, the distance between the values of the function at x1 and x2, so that would be x1 squared minus x2 squared, absolute value around this. So this distance is less than epsilon. So as soon as the distance between x1 and x2 is less than delta, the distance between the values of the function at x1 and x2 is less than epsilon. All right. So at this point, sometimes students would come to my office hours and say, well, what do I do? Where do I start? So we are just going to consider this statement, what it is that we need to show, right? We do not know that this is true, but this is something we need to show. So we are just going to look at this statement, and it's going to guide us in how to proceed. So we are going to have to show that there exists delta greater than 0. So so far we have no clue what kind of delta that's going to be. So we're just going to take a positive delta, and we are going to choose what that delta is going to be later. But so far we just want to have a number delta to work with. So let delta be greater than 0 to be chosen later. Okay, now let us take 2 points, x1 and x2, on the interval 0, 1. So let x1, x2 be 2 points on the interval 0, 1. And they are such that the distance between them is less than delta. Now remember, we still don't know what delta is going to be, but it's just some positive number. So we are taking 2 points on the interval 0, 1 such that the distance between them is less than delta. So then we're going to consider the absolute value of x1 squared minus x2 squared, and we are going to try to estimate this. So then x1 squared minus x2 squared, so this is going to be x1 minus x2 times x1 plus x2. And so why are we writing it in this way? It's because we know that x1 minus x2, the absolute value of x1 minus x2 is less than delta. We don't really know what this is. So the idea here is, I'm just gonna use some scratch here. So the idea here is that we are going to take x1 squared minus x2 squared. We are going to take a modulus of that, and we are going to make it some less than some kind of function of delta. And then we are going to choose delta so that this function of delta, whatever it is less than epsilon. And so, of course, if this f of delta is less than epsilon, then we can go back in here and say that this is going to be less than epsilon. So our goal for now is going to be to estimate x1 squared minus x2 squared absolute value by some kind of expression that depends only on delta. Okay? So that's the end of Scratch, and we are going to come back to our statement here that we have started to do. So x1 squared minus x2 squared is x1 minus x2 times x1 plus x2. And we already mentioned that x1 minus x2 is less than delta. So this is less than delta times x1 plus x2. And I'm going to continue after the scratch. So here we use the triangle inequality. Remember, we want to estimate this expression from above by some function that depends only on delta. So this is less than delta, absolute value of x1 plus absolute value of x2. Remember, by triangle inequality, absolute value of x1 plus x2 is less than or equal to absolute value of x1 plus absolute value of x2. Now we know that both x1 and x2 are in the interval 0, 1. So we are going to use that here. So x1, absolute value of x1 is less than 1, and the same is true for absolute value of x2. So this is less than 2 delta. Okay, so that's excellent. Now we want 2 delta to be less than epsilon. Remember, this is from our strategy, right? So now we have, this is a function of delta. So we want to make this function of delta less than epsilon. So this finally gives us a way to choose delta. Remember, we initially we said that delta greater than 0 is to be chosen later. So now we actually have a way of choosing this delta. So now all we have to do is to choose delta so that 2 delta is less than or equal to epsilon. And the reason why we can write less than or equal to is because we already have a strict inequality here. X1 squared minus x2 squared is going to be less than epsilon even if 2 delta is equal to epsilon. So, for example, we can choose delta equals to epsilon over 2. And I'm writing here, for example, because we could also choose delta equals to epsilon over 4, right? But I'm just going to do epsilon over 2. Okay, so then by the chain of inequalities above, so I'm going to denote this chain of inequalities by 3. X1 squared minus x2 squared is less than epsilon. So we really did prove what we intended to prove in the beginning. So let's just go back and make sure that we proved everything that we intended to prove. So we were supposed to show that there exists delta greater than 0 such that for every x1, x2 in the interval 0, 1, as soon as x1 minus x2 is less than delta, x1 squared minus x2 squared is less than epsilon. Let's just verify that we indeed proved that. This is a very good thing. Sometimes I read homework assignments from students, and it's sometimes the proof is kind of in the right direction, but it's not worked out all the way through. So this is why it's so good to write down what it is that we intend to show, so that at the very end, when we think that we have already finished, we can go back and verify that we indeed have shown what it is that we intended to show. So we needed to show that there exists delta greater than 0. So that delta is going to be epsilon over 2, right? So we fixed epsilon greater than 0. And so the delta that exists for that epsilon is epsilon over 2. Remember that we fixed epsilon greater than 0. So then we choose delta to be epsilon over 2. So then, as soon as we choose x1 and x2 in the interval 0, 1, if the distance between x1 and x2 is less than delta, which is equal to epsilon over 2, by this chain of inequalities 3, we see that x1 squared minus x2 squared, absolute value of this difference, is less than 2 delta. But then 2 delta is equal to epsilon. So this x1 squared minus x2 squared is indeed less than epsilon. And this is exactly what we wanted to prove. So this finishes our proof, and we can go ahead and write down the very satisfying thing that is very nice to write down when you finish a proof, QED. And remember, QED from Latin, it means this is what we